So, tutorial 2 from last Thursday, guys, the tutorial was not really canceled, just moved online in some way, right? So I really got the materials there already for you. So please make sure you take a look, the 2D array exercises and also the constant increments dynamic array. So that's something you must really make sure you go through before this Thursday, because I'll talk about another strategy for dynamic array, which would be a little bit more complicated to really analyze. But if you really got part 1 properly studied, I think you'll be okay for part number 2. Make sure you actually study for that, and if you got any struggle, you can let me know, okay? And for the asymptotic analysis, like section 2 for the tutorial, I think I'll give you the solution a bit later, but they should be quite straightforward. But I gotta give it a try, okay, on this. And the math review slides, well, make sure you really study that, because throughout the course, I will actually have to use the syntax from there to really explain some concept, you know. So you want to make sure you actually go over them, okay? Any questions about the course? Right, again, just be reminded, the first assessment is not coming until after the reading week. So please make sure, keep steady study. Don't really wait until the last minute or just for the reading week, right? I'm pretty sure you got other things to do during the reading week, not just for this course, okay? All right, if no further questions, let's now do a very quick recap and then we'll move on. All right, so think from last time, it's really just about the properties for big O. That's something you guys would have learned from 2101, but you know, a very important part of this course is to review what you study from 2101. So this is just about the proper subset relation between the family of the big O, right? We talked about the whole story from last Wednesday. So please take a look and refer to the recording if necessary, right? And then we just spoke about, why this is the most accurate and correct option to actually choose whenever you talk about something that's strictly lower power and something that's strictly higher power, right? That's something we spoke about last time. Just make sure you understand why we should really use this one here instead of this one here, right? There's a reason for that. And then we spoke about, proper subset, and then let's see, this is just about, if you actually got this particular relation, right? It doesn't really matter. Let's say, for example, if you got 3n, you can see 3n belongs to this big O family, but not this one over here. So that means, doesn't matter if you choose this one to be g of n, doesn't matter how large the c might be you choose, it doesn't matter. So it just cannot work as the upper bound multiplicative constant, right? Just remember that. All right, so that's another kind of exercise just to make sure you understand. Whenever you want to talk about asymptotic upper bound, you should really talk about the tightest one possible, right? If you talk about something that's too loose, because every algorithm, you can say it's exponential, 2 to the power of n. It's correct, but just not accurate, right? It can really mislead you to some wrong conclusion, right? So make sure you also go over this example here very carefully, right? And then we talk about arithmetic sequence. Over here, you just have some common factor, and we're going to see another quick example, maybe 1 or 2 today as well, when we talk about selection sort, insertion sort to conclude the review on asymptotic analysis, right? Just review the arithmetic sequence sum. And the way I remember it is, you just got to make sure first term plus last term, and then figure out how many terms you have, right? So when we talk about interval here, to figure out the size of the interval is going to help, right? That's something you want to keep in mind. And that was the last example we did last time, triangular sum. The most important thing is, when you look at the code, we're going to do something, again, very similar for selection sort. So if you look at something like this, right, you want to somehow analyze the nested loop over here, and usually you might get more than one loop counters. In that case, study the pattern of the combinations between the loop counter value. We're going to see something very similar, but not exactly the same. We'll see, okay? So you have to somehow use a table to study the pattern. That's the best way and most precise way to see what's going on. And then from there, figure out the equation, right? You can go through the details. Yeah, I may not repeat right now, but let me know if you got any trouble understanding it, okay? And then, right, so that's the idea about dynamic array. And your tutorial number 2 from last Thursday is about this particular strategy. It turns out this strategy over here doesn't matter if you use the worst case running time or average case running time. It's not really going to improve the matter too much. Okay, I will try to make it more precise when we get to the tutorial on Thursday. But on this Thursday, we are actually going to look at this strategy over here. It's pretty cool to really see that. Of course, the mathematical part we have to really go through with you very carefully. And then the conclusion is this one here, asymptotically, is simply more efficient, average case-wise or amortized case-wise. That's something we'll see this Thursday, right? I'll leave the details to Thursday, right? Hopefully no snowstorm this Thursday. So we're going to see each other in person, right? I think the first snowstorm is too early for the winter, just too early. Okay, that's about tutorial. Questions, please. Also, okay, so the plan today, I want to finish the asymptotic analysis lecture just by talking about selection sort, insertion sort, more like a case study, right? I'm pretty sure you have learned it before, but could be giving you some new perspective, right? We'll talk about it first, hopefully 20 minutes or 30 minutes maximum, I'm hoping. And then we'll start a new lecture. I'll get to the new lecture once we get there, right? Let's finish off the asymptotic analysis. Right, so if you look at the slides, it's really slide number 29 that we are talking about over here, right? Could be some stuff, might be basic, but I want to make sure everybody, is on the same ground. So it could be some basic stuff we have to repeat, but we'll try to make it smooth. Okay, the sorting problem. Given some sequence, let's say in this case array, you got to return an array that's kind of sorted in a particular order, right? So in here, we actually say it's going to be in the non-descending order, all right? So this is something I also want to review the basics. I think that's very important. Non-descending might be the most common order you will actually see. For example, 1, 2, 3, 3, 4, you see on the slide. Between 1 and 2, it's strictly increasing. Between 3 and 3, it's simply equal, right? So how do we relate the pattern over here of the numbers with the name, non-descending? You might see other sorting order. For example, you might see something like non-descending is 1, maybe ascending or increasing, non-ascending, and also descending and decreasing, right? So these are at least 4 possibilities, right? So it depends on exactly how the question is phrased. You have to know accordingly how you adjust the operation, right? So we're going to go over these 4, right? But of course, you might just be able to tell the distinction already, maybe, but let's review, okay? Let's review this order very quickly, and then we get to selection sort, insertion sort, okay? The best way to really talk about it is to choose any arbitrary 2 elements that are adjacent to each other in the sequence and see how they are related to each other, right? So let's start with this. This one here, and also, this one here and this one here are straightforward. When you get a none over here, you might need to apply a little bit of reasoning there. Okay, let's see. So let's talk about decreasing or descending. Okay, so this one here simply means the trend is going to go strictly descending, right? It's decreasing. So if you choose maybe index I from the array and also the next element adjacent, the next one, A at index I plus 1. If you try to relate these 2 elements together, apparently you can see that this one here is larger than this one here, right? Larger than. So this decreasing, descending really correspond to larger than. Example, so let's say 5, 4, 3, 2, 1. And if you look at that, for example, 4 strictly larger than 3. Very straightforward. And it's symmetric for increasing and also ascending. That one there, the pattern will be exactly the opposite, right? So again, if you choose an earlier element at index I, and the immediately element that's after that, A at index I plus 1, relation is going to be flipped. It's now going to be less than. All right? So let's say 1, 2, 3, 4, 5. And if you look at that over here, right, it's exactly less than. Okay? From before, it's greater than. Very straightforward. What about non-descending and non-ascending? Those ones, not really tricky, but just give you more possibility. Okay? So the way to think about it, I like to make things a little bit more formal, right? Because it can be very precise. Let's talk about non-descending. You know what descending really means? Non-descending simply means it is not the case, it's descending. Everything else is allowed, as long as it's not descending. Okay? So think about the none over here. And we can work it out. Think about a none over here. It's the logical negation, right? That's also part of the math review lecture. And the not here is logical negation. Okay, let's work out this, and then we'll see. Okay. So when I talk about non-descending, okay, so think about the none over here is the logical negation, right? By definition, okay, so when I say triangle equals, simply means that by definition. So this symbol just a kind of standard, right? Just by definition. Non-descending is not the case, descending. Not the case, descending. And let's now work it out. We know what descending really means, which is right here. That means we got not the case. Descending means the two elements will be A at index I strictly larger than A at index I plus 1. Right? Distribute the negation to larger than, you get less than or equal to. Right? Simply larger than is not allowed. Less than or equal to is allowed. Right? That's the way to think about it. So that one there is going to boil down to equivalent to A at index I less than or equal to A I plus 1. So that's the ultimate answer right here. So that means from between the two elements, you can either say less than or equal to. Either one is allowed. Okay, example right away. Okay, so when we talk about non-descending, it will look like something like this. You might actually increase. Oh, actually, let me just say one more thing. I think that can also help you. You can think about this one here means ascending, right? And this one here means flat, no change. All right, either way is okay. So now I may have ascending this way here. I may get flat. I might also get ascending again. You can keep repeating. The extreme case would be, let's say you got an array with all the elements the same, just flat, right? All right, so that one there. So you may have, for example, A at index I, and then I plus 1. In that way, you got ascending, so less than. Or you might get the next one, I plus 2. In that way, they're equal to, right? Just example quickly. So let's say 1, 2, 2, 3, 4. You can see this part here is flat, and this part here is ascending, right? What about non-ascending? Symmetric, right? So let me show you another way to understand it. So non-ascending means either descending or flat. Descending or no change. NC, no change. All right? So it could be that you can be descending and no change, and also descending. All right? So AI plus 1, AI plus 2, right? You got basically descending and also equal, right? Okay, example quickly. So we got 4, 3, 2, 2, 1. This part here is descending, larger than, and this part here is flat. Okay, so this is flat, and this is ascending. Right, it's a very quick clarification about these four orders, right? So that means, for example, we're going to talk about selection sort and insertion sort today. That one there assumed that we actually got non-descending order. But you may want to think about how can I implement selection sort, insertion sort if I give you a different order. That's one thing you may want to explore yourself, right? Okay. Let's now talk about the two sorting. So this one here is also a very nice review about when you want to work out, let's say selection sort. I'll get to the diagram, right? Usually in 2101, I might just build out the diagram from scratch. But you know, for 3101, I assume you have some recollection maybe from before, so we can start a little bit quicker, but it will still be informative. So for selection sort and insertion sort, we're going to do two different ways to derive the running time. One way, we don't need to see even any pseudocode or Java code at all. All we got to do is we somehow try to document the critical steps for the algorithm, and then we try to sum up the running time together. Right? So that's the approach number one we're going to see. Approach number two is you will just be given some more or less very precise Java code or pseudocode, but most likely Java code for this course, right? To see how to figure out running time. But let's do approach number one. Okay. And selection sort. Well, the name actually comes from the fact that you're going to split the algorithm into iterative steps. There will be multiple steps. Each step is going to involve mainly about selecting. Okay, you're going to select the minimum. Okay, of course, on the other hand, if you think about insertion sort, you're going to somehow insert, right? In the case of the selection sort, selection is the more costly part. It's going to dominate the running time. We'll see. In the case of insertion sort, the insertion step will dominate the running time, which we'll see as well. All right? Let's just use this example here, right? The convention is I'm just going to somehow color the sequence, let's say the array, right? In the beginning, input, I simply say everything is red. Red simply means it's unsorted. You can think about the initial unsorted portion covers the entire array. Ultimately, we want the array to be fully sorted. So everything is green, right? We want to evolve from input to the output, right? That's convention, right? Let's use this one here to see the steps. We can review quickly, and then we can generalize it, and then work out the running time, okay? So this one here. So we start with this input over here, and then we select the minimum, all right? So this step over here, we can document right away, right? You can think about this one. This step number one is going to help us to evolve from this input into this intermediate array, right? The same array, really. I just draw a different array to show you the steps, okay? So this step number one over here is going to correspond to, we want to select the minimum from index 0 to index, the last index, 3. Basically, select the minimum for the entire array. Select the minimum. All right? And once we have selected the minimum, as you can see, it is this one here. Right? So that's the minimum right here. So conceptually, we simply want to make sure this minimum here should become the first element in the green sorted portion. That's conceptually. And we're going to want to grow that green portion gradually. You can see we're going to grow from, think about initially the green portion is simply empty, no green. And then we expand it into 1, and then expand it into 1 and 2, expand it into 1 and 2 and 3, etc. But how do we implement this, right? If I find that this is the minimum, what will be the most efficient way to make sure this 1 becomes, let's say here, the first elements in the green portion? The answer is you have to do a swap. All right? So now in this case, okay, I'm going to document it, and then we can just do a few more steps. You can see. So this is the minimum. So we know that the next element for the sorted portion is going to be at index 0. So we're going to do a swap. That's something you will see in the actual Java code. And I'm pretty sure you know how to swap two variables, right? You just need a temporary variable and then just swap them, right? You will see that, right? That one I don't need to bother you. Okay. So after this swap over here, you can see 1 is here, 3 is here. So now what we have got after step number 1, guarantee the very first element or the leftmost element in the sorted portion is the minimum of the entire array. And we're going to keep going about this selection until the green portion is going to occupy the entire array. Right? It's more like, it's a very standard, like iterative algorithm. Right? When we talk about looping variants later in the course, we can revisit this example to see that as well. But for now, we don't need to bother. Right? Just get some intuition. Okay. All right, step number 2. So now we consider, so now that 1 is already off the hook, right? It's excluded from the selection. So now we're going to select the minimum from the unsorted portion right here, right? So step number 2 is going to be right here. So this will be step number 2. And then we're going to select the minimum from A1 to A3. And notice that we always actually want to select all the way until the end, right here and here. But this part over here, A0 and also A1, they will actually be a little bit different, right? Because we always want to select from the sorted portion, unsorted portion, right? Okay. And let's see that one there. So now, minimum, would you agree, is 2, right? So now the minimum is actually 2. 2 right here. And now what should we do? 2 is right here, and then we know that in order to grow this sorted portion by 1, this has to be containing 2. So swap these two, right? And then we're just going to swap these two. Okay, I'll just put a swap over here. And of course, if you want to write a Java code for this, you got to be very cautious about to keep track about where to really do the swapping, right? That's more like an implementation issue. I'll leave it to you, right? You can look at the code and study for that. All right, so after we do the swap, you can see 2 is now here and 3 is now here, right? We have grown the sorted portion by 1 and shrunk the unsorted portion by 1, right? Just keep going, okay? Okay, let me just finish the rest, right? So now this one here will be the 3rd step, and this will be the 4th step, right? This will be the 3rd step, and this will be the 4th step. Let me be a little bit lazy here, right? The 3rd step, we're actually going to select in a strictly smaller portion, which will be from A2 all the way to A3, right? And then in the last step, we're only going to select from right here, conceptually. Of course, you don't have any selection if the portion has only one element, right? Okay, so this one here, you have to select from A2 all the way to A3. And the last step, you're basically selecting from A3 all the way to A3. Okay, so you can see that we are really trying to moving towards the right for the selection starting point. Okay. Question so far? That's how selection and sort works. You basically got to do selection and also swap. All right. Let's now generalize it. And then we can work out the running time from there. As you can see, so far, there's no Java code. You don't need it, right? All you got to do is make sure you document all the critical steps. Okay? First of all, how many steps in general? Of course, there might be different variants about how you do the selection. So let's say, according to how I described, how many selections do we need? The length plus 1. Okay, that's interesting. If you think about, okay, let's double check, right? In this particular case, we do 1, 2, 3, and 4. 4 selections. But the length is 1, 2, 3, 4. Right? I mean, you know, in this case, unless I really ask you to really state precisely, otherwise -1 plus 1 asymptotically is not going to matter too much. But that's one precision. Okay? Okay, the number of steps is going to correspond to the size of the ultimate sorted portion. Think about after step number 1, we got size 1. After step number 2, we got size 2. After step number 3, we got 3. And after step number 4, we got this. If the input size is n, it should be n steps. Each step is going to grow the sorted portion by 1 element. Okay. Okay, so that one's going to be about n. Okay, so let me highlight it. It's a very critical facts. And then the selection, the cost, is it going to be increasing or decreasing? Decreasing, right? Good, because in the very first array, that's going to be entire thing, right? We're going to select minimum from the entire array. That's good. So now let me generalize it, and then we'll calculate it, and then we'll move on to insertion sort. Think about, let's say this. We start with an array of size n in general, right here. And then we have the size being n right here. And then let me create possibly a few. Okay, let's say 1 here, 1 here, and then 1 here. Okay, let's say ... And then finally over here. So all the arrays are equally long, right? They're the same length. Okay, I'm just showing different intermediate steps. And we know that this final thing is going to be all sorted, right? It's also of size n. And then after the very first step, I know that this part here is going to be sorted, and this one here is going to be unsorted, right? And just do one more. After the second step, I got the first 2 elements sorted. and the remaining part unsorted. Okay, let me just use a consistent color over here. And then, so let's see here. So this will be n minus 1, n minus 2, etc. Right? Let's talk about the very last step. That one there is going to choose from where we got only one unsorted portion. That one there is going to be unsorted, and the remaining part is already sorted. All right, like that. Right? That's the way to generalize it. Right? And here can be arbitrarily big. And talk about cost before we sum them up. So let's start with, let's say here, for step number 1, the selection part is going to be n, would you agree? Because I'm going to choose the minimum from an array of size n, right? Minimum, it could be all the way to the array that has the minimum, right? That the cost is n. And we're also going to do the swap. The swap between two variables, you just need 3 assignments, right? If you're not exactly sure which 3, you will see that in the Java code, right? That's going to be constant. And then the second step right here, that one there, the selection part is going to be n minus 1. Agree? Because now we got one less element to worry about. That one is already being put into the sorted portion. Okay? So n minus 1. And the swap remain to be constant, right, etc. And this very last step, selection part will be 1, right? And the swap, just 1, okay, conceptually. Okay, so these are all the steps you got to worry about, right? To go from here to here. And if you like, this will be step number 1, step number 2, all the way to step n. Let's now sum them up. All right? I'll write it on the top. I'm kind of running out of space. It's going to be big O. And then we know that, oh, I don't need this anymore. You know what green and red really means. Okay? So let's start with, let's try to split, let's say, separation of concern. Let's separating between swap and select. Okay? How about just swap? Each swap is 1. Okay? This will be the swap. How many swaps do we have to do? N, right? Exactly, right? Because we got n steps all the way, right? Very good, right? And then plus, all right? So now, how do we sum up the selection? We have to look at, right? This is something very similar to what we did. We got n minus 1, all the way down to 1. Arithmetic sequence, right? So that one there is going to be here, n plus n minus 1 plus all the way to 1. Okay, so you can think about this is the first selection. And this is the last selection. Okay, add them up together. Yeah, we can do a little bit of simplification. This one here, just n, and plus, okay, the beginning plus the end divided by, multiply n terms divided by 2, right? You can do beginning plus the end, we got n terms divided by 2. Of course, that's simply n squared. That one you don't need to simplify any further. Okay, so this part over here is simply n squared. N squared is going to dominate over the swap. So selection, that's why it's called selection sort. Selection steps is going to be the dominating factor. Okay, so finally, we got big O of n squared. Okay, that's the final outcome. I think the most important thing for you to really pick up here is you don't really need to see the pseudocode or Java code in order to actually figure out the running time. Right? We'll do something similar for insertion sort. Okay. Question? Good? Okay. Okay, so insertion sort. A little bit different, but similar, right? eventually it's still going to be a big of n squared. But this one here is conceptually a little bit different. Okay? Thinking this way. What's really going to be the same is we're still trying to start with maybe some unsorted array. Eventually, we want to get it to be sorted. That concept is really the same. But it's really about, for each step, what exactly do we do? So now we're going to do insertion as the main step. Okay? Let's take a look. So here, I didn't really start with, like the array being completely unsorted. I just start with at least one element has been sorted. So this is just like a variant. I want to make it more corresponding to the Java code I give to you, right? But you can feel free to really correct this concept here to say you can still start with the unsorted portion being the entire array and go from there. Just one more step. It's not going to change the running time overall. Okay? You can feel free to do that. So what we assume is we got one sorted portion, size 1. Array of size 1 automatically sorted. All right. So now insertion sort is going to go like this. So first of all, let's now go for select insertion. What we're doing is choose the leftmost element in the unsorted portion, and then try to insert it into the sorted portion in a way the grown sorted portion remains sorted. That's what's going to happen, right? So let's see. So we're going to insert this element here, A at index 1. Right? Let's try to see. Currently, the sorted portion is of size 1. I want to somehow grow it into size 2. So now 1 has to go in a way so that the sorted portion it will remain to be non-descending order. So that means I got two choices. I can either insert it here, or I can insert it after 3. In this case, it's going to be before 3, right? So that's why you see that 1 is here, and 3 is here. Conceptually, it's very easy. So because you know that 1 has to be inserted into here so that it remains sorted, so it'll be 1 and 3. But in the code itself, it's not as trivial, all right? So let's say in this case, I know that 1 somehow is actually going to go to here, all right? So that means whatever that is here, could be more than one element, I somehow have to shift them all the way to the right by 1 position. That's something you will see as the sorted portion grows larger and larger. That's why the insertion is going to be more and more expensive along the way. Okay? Keep that in mind, that insight. We'll revisit that. Okay? So you can think about what's going to happen is this part here is more like a shift. We're going to shift this element here to right here. Okay, so this is a shift. There might be more than one shift you have to do, in which case, in the worst case, you might be very close to the size of the array, right? That's why you will still actually have something that's not that, it's not just equally expensive as the selection sort. Okay, let's do one more. Okay, and then here, the leftmost in the sorted portion, unsorted portion is 4, right? So we want to insert A at index 2. We want to insert this one here into this sorted portion. Now this is this is not the worst case. This is a very good case because you don't need to do anything, right? So somehow you can see 4 happen to be the maximum in the sorted portion. That's okay, but we talk about worst case, right, in general. So it can be just 1, 3, and 4. No shift need to be done. Okay, so far so good. Let's do one more, okay? And then we can say to go from here to here, we actually go insert, and we choose the leftmost element, which is here, right? A at index 3. So now here comes the critical thing, right? And they will generalize it. We're saying we want to insert 2 over here into this sorted portion. Conceptually, it should really count somewhere in the middle, right here, right? So that'd be 1, 2, 3, 4. So that means you have to put 1 here remain the same. 2 here should be inserted. 3 and 4 somehow has to be shifted to the right by 1 position as a block. Right? That's the tricky part, but I'll generalize it. Okay? So this part here, you can think about index 1. What used to be index 1 is now going to be index 2. What used to be index 2 is now index 3. Right? Shift. At least get some idea about how the shifting should be done. But let's now try to generalize it. Once we generalize it, I'll show you another way to work out the running time, right? You can use a table, okay? Okay, so let's talk about insertion. The worst case. So the worst case for insertion. Okay. Let's say we have some intermediate array for us to start for the current step. And this will be the outcome for that particular step. All right? Over here. And then let's say this is the sorted portion. Sorry, beg your pardon. Let's say this part here is unsorted portion, right? Which means we're going to select, I beg your pardon, I shouldn't say select, I'm going to choose that one, right? I don't want to use select, that can confuse you. Let's take the leftmost elements in the unsorted portion. I take that, okay? And then we're basically trying to insert it into this sorted portion in such a way that we can grow the size of the sorted portion by 1, right? But now the question is, where should this element go? Now we are thinking about worst case. What will be the worst case here? The worst case, in a sense, that is going to trigger the most number of shift. Go ahead. Yeah, if this element that we want to insert happens to be the minimum for the new sorted portion, right? Good. So think about if this one here will happen to be the minimum compared with the existing sorted portion. Okay, so that one there is going to be here. And then in that case, you're actually going to shift this entire thing to here using a for loop, right? I'm pretty sure you know how to do it, right? Index 1 to index 2, index 2, index 3, etc. Okay? So that one there is going to be right here. Okay? So we can think about this will be some size. Okay, think about this like a size I, and the cost of shifting the entire block to the right by 1 position. The cost will be I. And I can be as large as n. So that's why this shifting part in the worst case might just be the size of the array. Okay, make sense? So now let's now sum up the running time. Okay. So what we'll do is let's now do several columns. Let's say we got step, and also which element should we get, like a pick for insertion. And then the running time for that particular insertion is going to depend on what's the size of the sorted portion, right? Depends on what's the worst case, okay? Size of the sorted portion. And once we know the size of the sorted portion, the worst case will be the element we want to insert happen to be the minimum. We're going to shift all the block, the entire block to the right by 1 position. And then we got the maximum cost for insertion. Okay, let's fill the table and see the pattern, and then we'll sum them up. Then we're good. All right. How many steps do we have, though? How many? If you think about this is step number 1, right here. Step number 2, right here. Step number 3, right here. It seems to be it's going to cover all the indices except for the very first one, because that one we assume is already sorted. Nothing to really pick from there for insertion. So for this particular case, we need exactly n-1 steps. All right? So that's something I can also say quickly over here. So think about right here, we actually got n-1 insertion. Okay, so we're going to get step number 1, step number 2, step number 3, all the way to n-1. Okay, that'll be the last. Let's fill out the row for the first and last steps first. Okay, the first one, we are just going to insert A at index 1, right? That one there. And the last step is gonna be we choose the last index right here, right? So that's gonna be A at index n minus 1. And the pattern goes on, okay? And the size of the pattern for sorted portion starting from 1. And then this one here will be n minus 1, right? Agree? Okay. So go from 1 all the way to n minus 1. Okay. Let's fill out the rest, and then we talk about the last column. The second step will be A2, A3, and it goes on. And the size will be 1, 2, and 3. Now you can see that this number here is growing. That means your cost about insertion is also growing, as opposed to decreasing cost for selection in the selection sort. That's another very important insight for you to compare the two. Right? Okay, the maximum cost accordingly would be, since I got sorted portion 1 here, so that'll be 1. 2 here, so that'll be 2, right? Depends on if that's I, the maximum cost will be just I, right? 3 here would just be 3. N minus 1 here would just be n minus 1, right? So now what we should do is we're going to somehow sum them up together. Okay? Okay, let's now do something very similar as before. Let me just delete this one here. Okay? So it's going to be big O. Over here. Okay, we know that we got n minus 1 steps. So n minus 1 steps, and then multiply by 1. That one there is really just about, choosing the very first element, from the unsorted portion, right? So this will be the steps. And this will be to get the leftmost from the unsorted portion. Okay, so this part here is going to be dominated anyway, but just write it down for completeness. And then we're going to sum up the cost for insertion. And these are the worst case for each insertion, right? So 1 plus 2 all the way to n minus 1. You can see the arithmetic sequence here is kind of the opposite as the selection sort, okay? The common difference, rather than minus 1, is now plus 1, okay? So it's going to be right here. 1 plus 2 plus all the way to n minus 1, okay? And of course, this part here, first term plus the last term, how many terms do we have? n minus 1, right? From 1 all the way to n minus 1. It will be n minus 1. And then divided by 2, okay? N squared, basically, right? So you can think about this part here, it's just n squared. This is n. N squared is going to be dominating. So big O of n squared is going to be equal to, okay, I'll just write down one more step, n minus 1, which is this part here, plus the n squared, which is the arithmetic sequence. Going to be big O of n squared. So selection sort, insertion sort, without seeing the code, we know that asymptotically they are the same, in the same family. Okay. Question? All good? Okay. So before we take a break, I would suggest, one moment. Let me pause the recording just for now. Okay, one more case study to do, and then we can say goodbye to the asymptotic analysis. Okay. So the next one I want to talk about, so these two are just based on conceptual understanding and some visualization, right? And now you do have the Java code, right? I'm going to make it available to you as well. You can play with it in the Eclipse, and I'll tell you some exercise to do. So now here, even if I don't tell you this is selection sort, in order for you to figure out the running time, you don't really need to understand the logic for the algorithm. So you can even say, this is just some method n. Now I'm asking you, what's the asymptotic upper bound? All right? But you can kind of guess, this is like a 4 and 4 nested, and somehow I got 2 loop counters in a way they're related like the triangular sum that we did last time. So n squared, that's a good guess. I will do the same. But now the second part is going to be tricky because you got to show your work, right? So that's the part I want to talk about very quickly, okay? So this one here is very similar, but just slightly more complicated, slightly, okay? So I'm going to do the stuff here. I already highlighted the 2 loop header, one here and one here, right? Let's worry about these lines, the rest. Here and also here, right? Let's talk about them, okay? It's important. Let's start with this. This one here is simply do some variable assignments. And when I actually sometimes give you some Java code on the slides, I just use the indentation sometimes to really mean the brackets. Of course, in Java code, you may have to put more parentheses or brackets, right? Just to remind you, okay? So indentation tells me that line number 6 to 8 are also at the same level, right? Over here. And you can see that this part here is just one variable assignment. And this part here is just about the swap I spoke about, right? So when you actually want to study about the meaning for the selection sort, you may want to trace this code a little bit. I do have some exercise for you and solution, okay, for later. And this one here is just about array indexing, variable assignment, etc., right? Cheap stuff, okay? Also one. Now the question is, how many times in total are they going to be executed for these two blocks? Does it depend on just I, or does it depend on J, or depends on both? Yeah, go ahead. Huh? Both. You can both? Okay. Oh, are you sure? I can let you correct yourself if you want to. No, I think it's better. Okay, so let's think about it, right? So here, I'm only asking about how many times they're going to be executed, right? You can see that this part here, this whole block from line number 3 to 8, they are the body for this outer for loop, which means how many times this will be executed depends on only the I, about how many times we're going to run the outer loop iteration, right? So that means this part here and this part here only depends on I. They might use the J value, yes, but how many iterations you're going to execute them only depends on I. Guys, it's a very important insight, right? So if you got trouble, you can let me know, okay? So these two, the number of execution, number of execution depends on the value of I, okay? And then if you look at this one here, line number 5, this one here is indented, which means it's going to be inside and in the loop. That would mean the number of times line number 5 is going to be executed depends on the pattern of I and J. So this will be very similar to the triangular sum that we did the other day. All right. And this one here itself is just 1. However, we've got to worry about how many times it's going to be executed. That's the main thing. The number of execution depends on the value of I and J, the combination. So that's why we're going to do that table again and then figure out. All right? Let's now do the table. Okay? Just one more exercise. Okay? So I can go a little bit quicker, right? You can tell me if there's any part you want me to slow down. Let's start with the I. It's going to go from 0 all the way to n minus 2, right? So it's going to go from 0, 1, and 2. I would suggest each time when you try to do the table, maybe do about 3 rows. I think that's about enough for you to see the pattern later. 2 or 3 values, but 3 would be more recommended. Okay, all the way to n minus 2, right? We can figure out right away how many iterations. It's going to be starting from 0 to n minus 2. How many? N minus 1, right? It's going to be n minus 2 minus 0 plus 1, the little formula, right? So this one tells you it's going to be n minus 1 iterations, okay? That's about the first dimension, okay, n minus 1. And then what about j? It's going to be very similar. J is going to be from I all the way to also n minus 1. So we got j here. So 0, 1, 2, all the way to n minus 1. And when I is equal to 1, it'll be 1, 2, all the way to n minus 1. I is equal to 2, it's going to be 2 all the way to n minus 1. N minus 2 is going to be n minus 2 and then n minus 1, right? Very similar to triangular sum, but not exactly the same. So you got to be very careful when you show the detailed work. Okay, so now we know that for every combination of I and j, for example, this and this correspond to one execution for this line number 5, right? Like what we said earlier. So now, let's now figure out how many times do we have to execute line number 5 here? It's going to be from 0 to n minus 1, which will be n, right? And here is going to be from 1 to n minus 1. And that one there is going to be n minus 1. This one here is going to be 2 to n minus 1, right? You can see it's a descending, right? n minus 2. How about here? What should I put? How many times are we going to execute line number 5 in the last row for n minus 2 and n minus 1? How many times? What should I put here? Anybody? I wouldn't mind a guess. 2. Okay, good. That's a good guess, right? Maybe just obvious to you. Okay, that's good. Okay, it's going to be just 2. You basically go from n minus 2 to n minus 1. All right, so that's what we have. Okay, let's now sum up the running time altogether. So it's going to be big O. All right. Let's talk about outer loop, because we know that this one here and this one here, they don't depend on the inner loop, right? And these two are together just 1. First of all, you can say n minus 1 times 1. Okay, so I'll write it down. You can think about this is the number of iterations for the outer loop. Right? Remember the number of iterations right here, n minus 1. And each iteration is going to execute this and this one time, right? So think about this one here is really line number 3 and also line number 6 to line number 8. Right? That's the first part. And the second part is going to be about the blue line, line number 5. That one there is going to be basically, okay, n minus 1 all the way to 2. N plus n minus 1 plus all the way down to 2, multiplied by 1, right? You can think about the 1 over here is really referring to line number 5. And then, what about this part? Arithmetic sequence. N plus 2, right? First plus last term. Multiplied by, how many terms do we have? N minus 1, right? Okay, I'll let you verify that yourself. Divided by 2, right? N squared, right? But at least you should really show up to here. Okay. So now what we got is, we got the big O of n minus 1, this part, plus n squared. It will still be big O of n squared. So you can think about, for the same selection sort, really. Either we give you the Java code, you figure out it's big of n squared. That one there, you don't need to know about the logic for the selection sort. On the other hand, let me just switch quickly. If you look at this one here, you have to know the meaning for selection sort about how it works. You can also work it out, the running time. Either way, we can work out the running time. All right. And I also gave you the Java code for insertion sort. All right. You figure out. Okay. Exercise. Similar. Okay. So this one here will be exercise for you. And before we take a break, you guys definitely deserve a break. Okay. Let's now just go to one slide for extra exercise. Okay, if you're not exactly sure about how selection sort, insertion sort really work in the Java code, you can refer to this slide here, just about tracing, right? I think it's a very foundational skill you shouldn't really abandon, even in this course, right? Take a look at the Java code, and then you can trace the code. So slide number 32 gives you all the resources. If you want to trace it together with me, you can also look at the video, optional, but at least you should know how to trace. Question? Okay, why don't we take a break and then we'll start a new topic. Okay. All right, so we are now done with the review on the asymptotic analysis. We've done many examples there. And also, the last example we will do is on the tutorial this Thursday when we do the doubling strategy. That'll be the last one, arguably maybe the trickiest one or the most more complicated one to get done. Okay. So you can review the slides, and then we're now going to start with the topic self-balancing binary search tree. I would say if you consider, maybe some of you already learned about maybe AVL tree, maybe back in your 2101. I think it depends on the instructor. Not necessarily that one will be covered, right? But I'm going to just teach you that anyway. The main thing is about tree rotations. But before we can even get to the tree rotations, I think it would be better to really review some basic stuff about the trees, sorting property, search property about the tree, and also balance property, etc. I'll try to do that in about within 1 or 1.5 lecture-ish. I'll start today, and hopefully we can finish all the basic stuff. Otherwise, it will be difficult for you to understand about why rotations should be done in a particular way. Okay, we'll go one step at a time. Okay, so the slide there is already on the lecture site. So we're going to talk about very basic stuff, linear versus nonlinear. And also, the most important definition to recall over here is called depth or heights for the tree, right? You may have, I'm pretty sure you have seen that, but let's recall the definition as well. And also, we got to talk about mathematical properties for binary trees, especially how can we somehow impose some upper bound and lower bound for like the number of nodes in the tree given some heights. Or can we impose lower bound, upper bound for the height of the tree given the number of nodes, right? There are two properties I would like to talk about. It's so relevant to rotations. And traversals, pre-order, in-order, post-order. I'll review, I'll do example for one of them. The other two, very similar. I will leave as exercise for you and give you a solution. And then we're going to get to binary search tree, of course. I'll review quickly about search property. And also, we're going to see how we can implement this in Java, generic. Okay? So this will be something you might have to do in the assignment, number 1, which you're going to release in time, and also in your programming test as well. Okay? That's something we're going to do. Okay? Okay. Hello, over there. Can you please take off your headset, please? I appreciate that. Thank you. All right, and then we're going to talk about when you do searching and what will be the worst case running time. It's going to be linear. I'll kind of briefly mention that, but we're going to see exactly how. That's something to do with the mathematical property. And also high balance property as well. I don't think we can get that deep today, but we'll get there eventually. And it's really about rotation. Oh, to do rotation, we also got to review about insertion and deletion for binary search tree. Okay, I think insertion is pretty straightforward, but we'll just do some example to review. But deletion, you have to talk about different cases for you to do deletion. That's something we'll talk about as well. There are 4 cases in total, but we're going to get there. Okay, and of course, the last bullet point here is really the main outcome, learning outcome for this lecture about rotations. But I don't want to go there directly. Let's do some proper setup for the context before we get to rotation. Okay. And the idea will be, once we finish this lecture about self-balancing binary search tree, hopefully within 2 or 3 lectures, and then we're going to move on to graph. And we're going to spend a lot of time on the graph. That's really the main thing we want to focus on for this course. Okay. Let's now, first of all, go for this one here. Okay, general tree, you can definitely read the slides, but I just want to clarify very quickly about linear and nonlinear data structure. Okay, let's talk about this first. So we talk about linear versus nonlinear. So you haven't really learned about the graph just yet. So I didn't really include any example. But let's just talk about what you know already. You got basically array, right, with indices. And also you got linked list, which can be either singly linked list or you got doubly linked list, right? That's what you learned from 2101. Okay. So when we talk about linear data structure, okay, what does that really mean? Linear, the way to judge whether a particular data structure is really linear, you want to look into the concept about predecessor and successor. Okay. So let me write down the definition criteria first of all. So it's going to be unique predecessor and unique successor. If you break either one of them, it's not linear anymore. If you think about it, it's De Morgan, right? If you say P and Q is a condition, what does it really mean? Non-linear, not P or not Q, right? Hopefully you kind of follow what I'm saying here. But let's talk about linear first, right? So how do we see predecessor, successor? Let's say in the case of the array, if I look at a particular index, right? If I look at this particular index here, let's say this is index I. If I try to go to I minus 1, so that will be predecessor. Okay? And I can go to the next one, which will be I plus 1. It's called a successor. Okay, we'll talk about immediately after or immediately before. There's a unique one in the case of array. So that's why array is a linear data structure. Obvious, right? Just checking the definition. And in the case of the singly linked list, there's no predecessor. There's no previous reference. That's okay. Just simply means there's no violation for the predecessor uniqueness. So this one here is a successor, right? You can think about this is the successor. That's unique. All right. And of course, for a doubly linked list, you can see unique successor given this particular node. Unique successor and also unique predecessor. They're also unique. All right? So far so good? Okay, it's about linear. What about nonlinear? Nonlinear, what we know pretty well from 2101 is if you actually break either of the rules right here, it's not going to be linear. Okay? The tree data structure we learned in 2101 actually break the unique successors constraint. Okay? How do we see that? You can see that given this particular node, for example, okay, so if I want to go for this way, so we say if you go to your child node, like go to like a lower level in the tree, right? We kind of divide the tree into different levels, right? I'll review the level as well, precisely, but you can think about this is what we call level number 0. This is what we call level number 1. This is what we call level number 2, and etc. Okay? So now, if I want to go from a particular node to its successor in the lower level, immediately lower level, I may have more than one successor, like more than one child nodes, basically, right? So that means for tree, I actually got multiple successor, like a left child, right child, for example. However, for predecessor, that one there is still like a unique, right? Because if I want to go, let's say from here, let's say I'm here. If I want to somehow work my way all the way to the root, there is only one particular we call ancestor path, which I'll review a little bit more later. If I start from here, the only way for me to go up is to follow my parent's reference. I can go here, and then go here, and then go here. So the parent reference is the predecessor. That's unique, right? But it's unique predecessor. Okay, so of course you can think about the successor in the case of the tree is the child nodes, children. And predecessor is really the parents. That's about the tree, okay? Hopefully that's straightforward. But the main thing here is know the criteria about judging if a data structure is linear or nonlinear. That's the main point, okay? And I want to give you a very quick look ahead. How about graph? Since the graph, okay, first of all, graph is also nonlinear. So tree over here is nonlinear. Graph also is nonlinear. And one example that we kind of saw, back in, let's say, to the tutorial or the motivating lecture, motivating problem, you can see that somehow we just get a network of the different objects connected together. So predecessor, successor, they're completely generalized. So you definitely got multiple for each. Okay? That's something I'll elaborate a little bit later, but I just want to write it down right here. So this will be multiple successor and also multiple predecessor. All right, multiple. You definitely break both rules for being linear. Questions? Okay, and then let's now move on. Let's now clarify some terminology. Okay. So let's talk about edge and path. I can do that quickly. So if you got a tree here, every time if you have between two nodes right here, okay, it's called an edge. And we're going to use the same terminology for the edge for graph as well. So you'll see the name edge too. And later on, when we actually want to program graphs, you will see that we have a class called edge as well. Okay, so it's called edge. And if you got multiple edges to really connect it together to go from one place to another, it's called a path. The most famous path, which we have to see when we do rotation, is something like this. Let's say I start with the bottom. Let's say Vanessa. To go from Vanessa to Elsa, that's one edge. To go from Elsa to Chris, another edge. Go from Chris to David, who is the root, that's another edge. So this part here, the path starting from Vanessa all the way to David, the root, is so-called ancestor path for Vanessa. Okay? So later on, look ahead, when we do rotation, the algorithm itself would say, let's say after you have inserted one node into the binary search tree, you have to go from that inserted node and go all the way up along the ancestor path for that particular node. So what does ancestor path really mean? You're going to keep following the parent references. That's something we'll see. Okay? So, and also when you want to program that in Java, that's something you have to follow as well. Okay? So this one here is so-called ancestor path of Vanessa. Right? To go all the way to the root. Okay? Okay, let's talk about depth and heights. Let's see the definition quickly. So we got general tree. Okay, so we got edges. Okay. Oh, first of all, let's start with the depth. It will be given a particular node. You want to know its depth. It's going to be the number of edges from the root to the node itself. And given the depth for each node, we can somehow divide the whole tree into different levels, like a hierarchy. Okay. Let's see example. Okay. Oh, let me just have a new page right here. So let me start with the same diagram here. Oh, sorry. Let me do it again. There we go. Okay. The same family tree over here. And then, for example, let's say just choose one. Let's say for the root. So you can see for David here is the root. The depth is simply 0. That means the number of edges from David to itself, the root, is 0. All right? And then for Ernesto and Chris over here, they have the depth being 1 because you can see go from Ernesto to the root, 1 edge. Go from here to the root, 1 edge, right? The depth. Okay? And then you can see that this one here, Elsa and Anna, so these are the nodes where the depth is simply just 2. Okay, finally, we got another level of nodes here where the depth is simply just 3. That's the maximum depth. Okay, so you can see for Shirley, it's going to be 1, 2, and 3. For Vanessa, it's going to be 1, 2, and 3, etc. So now if you try to categorize the nodes with the same depth, we can categorize them you can divide the tree into levels. So now, what we have is right here. We say level 0. And the 0 here corresponds to the 0 here. And this will be level 1, correspond to 1 here. And also level 2, correspond to 2 here. And also level 3, and then here. All right, let's write down some nodes, and then we'll get to the heights. The depth of a node n will be the number of edges Or you can think about edges simply the links for the parents. From that particular node n to the root of the tree. All right? The depth is very straightforward answer. You can define the depth for each node. So now a closely related definition will be about the heights. You don't really say the height of a node. You only say a height of a tree or a height of the subtree. Okay, let's see example. Okay, all right, let me write it down first. And you will see also the same definition on the slides. And the height of a tree or a subtree. Okay, so here comes the definition. And we'll try to maybe do some programming exercise, possibly this Thursday. We'll see. Okay, it's going to be the maximum depth of descendants of its root. So this means if I got a particular tree, let's say, or particular subtree, consider all the nodes in that particular tree, and then figure out all their depths and choose the maximum. That's one way to think of it. However, we're going to have a slightly more efficient way to figure out the heights, like a bottom up. Okay, that's for later. Okay, I'll put the nodes right here. I'll put the note maybe next time. Okay, that just saves some time. I want to do one more example quickly, and then we're good for today. Okay, so let me again try to copy this one here. Okay, I'll do one more page. Okay, I'm going to show you the idea about the heights. There we go. Too big. Okay, so here, let's figure out the heights for two different trees. Okay, let's start with the whole tree. So I'm going to say the heights of the tree rooted at David. So I'm really talking about this whole tree. What I should do? Figure out the depth for each node. And we know pretty well from before, we start from top down. Depth will be 0, and these two, the depth will be 1, and these two, depth will be 2, and also these three, the depth will be 3. Maximum. Basically the depth for the lowest node. Okay, so this is the maximum. Okay, should be 3. All right, let's do one more. Okay, the heights may not be just about a particular, let's say the whole tree. It could be about a subtree, which will be useful when you do recursion later. So now if I say the heights of the tree rooted at Elsa. Okay, so you can see Elsa is here as opposed to David from before, right? So that means we're constraining ourselves to just this particular subtree. In that way, we have to annotate the depth accordingly. Okay, so something like this. We're going to say depth over here will be 0. You can see 0 as opposed to 2 because we got different root in the context, right? Over here, we got the depth here will be 1, accordingly the depth and the depth. So what will be the height for this subtree? 1, right? That's a maximum. Guys, any questions so far? All right, I'll stop here and then we'll continue with this and then we'll do more mathematical properties on Wednesday. Okay, see you later.